Last time we discussed the following differential equation. And we built the bounded solutions. We found one bounded solution, one unbounded one. And so here is how it looked like. So the general type, the general contour representation of the solution was as follows. And the V function was the following. And we chose the branch cut and the corresponding contour as a finite segment. So what we'd like to do right now is we'd like to discuss just some more general properties of the solution. And for example, last time we addressed the case when x was positive. The question is, what's going to happen with the solution when x is negative? So how the asymptotic of the solution changes. Right, so last time we discussed in great detail the solution. It happened to be finite, which a bounded solution at x tending to plus infinity and at x tending to 0. So the solution was defined by the following contour. And now, but the most interesting thing which is happening here is when we discuss another solution defined by this contour. Right, so let's actually discuss this in some detail. So this contour is good only when x is positive. Why? Because this V function, it vanishes at point t is equal to minus I, and then at t tending to minus infinity as long as x is positive. But when x becomes negative, then this direction is no longer a good one, right? In fact, the contour may go to infinity in the whole left region of the complex plane, right? Because the condition for the decay of this factor, for the decay of this exponential, is as follows. The real part of xt is negative, right? So when x is positive, then t, the real part of t, should be negative. Right, so the allowed region in which this contour could flow from this minus I point is there, this entire complex plane. Now, we'd like to ask ourselves, what's going to happen to this solution when we, for example, x goes from plus infinity to minus infinity? For example, here is our, well, actually, it's better to go from plus infinity to minus infinity even in the complex plane of the variable x. So here are large positive x, here are large negative x, and say we go from large positive into large negative x via the upper complex semiplane, like that. So x changes to modulus x times e to I pi, right? And here, for example, when x is here, it's simply modulus x times e to I phi, where phi changes from 0 to pi. All right, so let's look at this condition. In fact, the reason why I chose the contour in the strict left direction is that this happened to be the steepest descent direction for when we try to estimate this integral, right? Why? Because well, it's obvious, right? Because the steepest descent direction actually defined by the condition x times t, the argument of x times t is equal to pi, right? And since the argument of x is 0, then the argument of t is pi, hence this direction. Now the argument of x starts changing, so now it's phi. So, and the condition is changed, so now the condition is, so the argument of x is phi plus the argument of t should be equal to pi. So the argument of t, if we are interested in the steepest descent direction, should be pi minus phi, where phi is the argument of x variable. Right. So when x is rotating counterclockwise, then here this steepest descent direction rotates clockwise. And you see that we encounter the problem when this phi reaches pi by 2 value, because then the steepest descent direction starts actually intersecting with the branch card. So the question is, what's going to happen if phi actually exceeds pi by 2 value? Then, because if phi, for example, is equal to pi, you clearly see that the argument of t, the steepest descent direction, its argument is 0, so it changes its sign completely. So it's the right hand, the right direction, this way. So something should happen with this contour, right? And now we are going to talk about this. So we are just discussing, we'll discuss it in some detail. So what is actually happening? But before we do so, let's actually just discuss normalization condition for our solution, because that's an interesting problem by itself, because we know that we discussed last time that the solution is unbounded at x is equal to 0, right? But what we can actually, how can we fix the normalization constant, for example? Well, we can fix it by imposing the condition on the imaginary part of u of x at the origin. And this u of x, well, it happened to be finite. And this is going to be our normalization for our equation. Right. So now we'll address this normalization later and fix all the constants, because here, as you remember, some constant is always present in front of our solution. Right. But let's concentrate on what is happening when x changes from positive values to negative values. So first, let's address the positive values. So x is positive. Then the asymptotic set large x is elementary to find. So what we do, so now you understand that it's defined by the vicinity of this branch point. T is equal to minus I. So we make an expansion. T is equal to minus I plus some small number s. And this s can be parameterized as rho times I pi. And rho changes from 0 to plus infinity. And this is how we estimate our integral. So u of x is equal to this constant a times the integral overall from 0 to plus infinity. dt is equal to 0 to e to I pi, so which is basically -1. And here we have e to ix, sorry, minus ix, times e to minus x rho. And then we have to expand, we did it last time, this denominator, the vicinity of this minus I point, and the expression gives us the square root of 2 rho. But what we actually need to be careful about is this phase, right? And we spend some time just evaluating the correct phase. Well, let's do this again. So our multivariate function g of t is defined in such a way that g of t minus 0. So when we are on the left bank of our branch cut, it's going to be positive when t belongs to the segment from minus I to I. So this is a fixation of the regular branch. Now we move in this direction. So our t plus I component, t plus I factor, changed its argument by pi by 2, plus pi by 2. So square root pi by 4, and we put it in their denominator. So it's going to be minus I pi by 4. So this, as you remember, this integral gives you a simple gamma function. And here is our answer. So the answer is going to be, the integral gives you the gamma function of 1/2, which is square root of pi. So we have here factor 2, so square root of pi by 2. Now, after the appropriate change of variables, well, we did this last time, you will get x in the denominator, and you'll get e2 minus ix minus I pi by 4 in the exponent of your exponential function. And naturally, you have minus sign and constant a. Right, so now let's see what's going to happen with this asymptotics when x changes from positive values, like big positive values, to big negative values.